Hey guys, what's up? Welcome to this video on constrained and unconstrained optimization in R. In this video, we're going to be talking about using optim and solnl to go and address these problems. Let's go. So this is a video on constrained and unconstrained optimization in R. Specifically, we're going to be talking about how to solve common problems from economics such as profit maximization and utility maximization using optim and solnl from the NLC optim library. Knowing how to use these optimizer commands is important because they are much of the backbone for computing economic models and generating data from them. We will discuss unconstrained optimization using optim by going and solving a profit maximization problem. Then we're going to be talking about unconstrained optimization using solnl. There we're going to be going and solving the same profit maximization problem just in the context of solnl. We're then going to compare the output from optim and solnl from both these procedures, and then we're going to be talking about a constrained optimization problem using solnl. In that case, we're going to be solving a utility maximization problem. So the profit maximization problem that we're going to look to solve is going to be the following, where we have to maximize 10x minus x squared minus 20, where x is going to be defined as the quantity produced by the firm. In order to go and solve this in the context of R, we have three steps here. We're going to first take an initial guess in our feasible region. Some people like to go and put this after defining our profit function, which is our second step here. And then we're going to go and solve it. And in that case, we're going to be putting in our initial guess in our feasible region, followed by our profit function. And then there's going to be three other arguments that we have here. The first one is this control is equal to list fin scale equals -1. This tells optim that we're going to try to maximize this problem and not minimize it. The next one is that we have this lower equal to 0. This defines our lower bound, where we want to go and have our optimum to go and exist, which excludes negative numbers. And this last one is method LBFGS minus B, which is a box optimization method here, and this is just to go and hide the warnings regarding using this optimization technique right here. Now, if we were to go and solve this problem using solnl, we're going to go and first note that there's a lot less code that we're going and looking at. But this comes at a cost of having to go and trick this function into doing what we want it to do. The way we do this is by instead going and looking for the minimum of the negative of this profit function subject to no constraint. So again, we have three steps. We have to take an initial guess in our feasible region. Step number 2 is that we're going to define the negative of the problem that you want to go and solve. So again, I'm defining this as invert profit, which is just the negative of that profit function. And then we're going to go and solve it by going and putting in guess or inverted profit and null, which is going to be this absence of a constraint. Now, when comparing output from optim versus solnl, we note right away that solnl gives you a lot more information and a lot more output compared to optim right here. We note that the actual maximizing inputs, which is what we're going and we're looking for here, they're going to be the same that we go and we have here, but the actual value evaluated at these optimums, they're going to be different. They're actually going to be opposite in sign because again, we've tricked solnl into going and finding this profit maximizing input. While under optim, we have not done any tricking. We just used in a built-in function. Likewise, if we go and we actually look at this Hessian command here, right, which is again just a singleton right here, we would go and note that this shows that our profit function is convex as opposed to concave. Moving on now to constrained optimization, we're going to be working exclusively in the framework of solnl because I found that it is actually the best for going and addressing these types of problems. The problem that we're going to be looking to solve here is that we're going to go and maximize a Cobb-Douglas utility function subject to a well-defined constraint here where we have an income of 100, our price on good 1 is 4, and our price on good 2 is going to be 3. Again, we're going to have to trick solnl. So we're going to have to go and invert this problem, right? Putting a negative sign in front of our objective problem and rewriting our constraint, right? Again, this is a strict constraint being equal to 4x1 plus 3x2 minus 100, and that's going to be equal to 0 because that's how we go and read in each one of these constraints. So again, solving this problem is that we're going to take an initial guess in our feasible region where our guess is going to be contingent on how many observations that we go and we have here. So again, I'm just doing one for x1 and one for x2. And then we're going to go and write our objective problem, which is going to be written as the following, which is just negative of our Cobb-Douglas utility function that we've defined here. Next is that we're going to define a constraint function. Now, the way we define our constraint function is that we're going to have to define a space where we go and we have it. So because these constraints are read in as a vector. So we're going to first define this null f, and then we're going to go and bind to it this constraint that we go and we have, and then we're going to go and spit out a list where we have some constraints which are going to be CEQ, which is going to be, they're not strict constraints. They could be greater than or equal to 0. And in our case here, we're going to go and have it where it's strictly binding. And then we're going to go and solve it where we put in our guess, we put in our objective, and then we put in our constraint. Looking at the output from that equation, we go and get the following, where we get nicely our utility maximizing optimums for x1 and x2 under this par argument that we go and have. The actual measure of utility, just like how we saw under our profit, that's going to be inverted, giving us a negative number. Our Hessian matrix will also be inverted because it's going to show it as being positive definite, which shows that it is a minimum because we've tricked our function here, when it's really supposed to be negative definite, where if we want that for our maximum. This is because, again, we've tricked solnl into doing what we want it to go and do. Bottom line, solnl is great for constrained optimization and getting answers to questions, but you need to be careful how you use it beyond just going and getting your inputs. So again, use it, trick it, but be careful. So that's all for right now. Let me know what you think in the comments below. Take care.